Okay, good morning. We're going to try this again because I apparently had messed up earlier. But exponential functions, growth and decay. We're going to write and evaluate exponential expressions to model growth and decay situations. And if you were in MMA, this should be something you've seen before. It's not anything that's very difficult. Okay, so let's look at a table first. You can see here I'm going up 1, 2, 4, 8, 16, 32. If I tried doing my normal rate of changes, I would get 1, 2, try the second ones, I get 1, 2. So those don't work because I tried doing here, like saying, since the first ones are all different, can't be linear. Since the second ones are all different, it can't be quadratic. I could try third one to see if it's cubic, but again, those would not work. And the reason why is because this one doesn't have a constant rate of change of any sort because it can be done through multiplication. If I multiply everything by 2, then I get, say, the rate of change here, which is everything's multiplied by 2. To show that, we don't do that the way we normally have. We do that through what is called an exponential function. An exponential function can be written in the form of f of x is equal to b to the x power, where b represents the base, the constant, the change, the whatever. So in this case, like in this last one, that would have been f of x is equal to 2 to the x power. That would have represented the function. That 2 to the x power, also notice the x there, your variable is now in the exponent. That also would represent the parent function. So with that, we get the parent function, which would create a 2 to the x power, and here's a table showing that. Negative 2 to the x power, 2 to the negative 2 would have been 1/4, 2 to the negative 1 would have been 1/2, 1, 2, 4, and 8. With the graph that you're seeing there being made, keep in mind that when you're talking about with negative exponents, again, look, notice how those come up with fraction answers. And what we would create here is what is called an asymptote. Notice also that the graph does not cross the x-axis. It creates what is called an asymptote. We've done those before. Those are lines that the graph gets close to but doesn't actually technically cross. So there's almost like there's a barrier there that they can get close to, but they can't get across. Okay, so how do we use this? Well, we're going to use the function to, first off, I would like to make sure that you can identify what are called exponential growth and decay, and that's pretty easy. You look at the number that's having an exponent raised to it. Okay, so like the one that has the x. And if the number is bigger than 1, that means it's going up, that's a growth. And if the number is between 0 and 1, notice no negatives, between 0 and 1, that's a decay, and that means it would be going down. Okay? So, for example, f of x is equal to, let's say, 1.5 raised to the x power. Okay, since the 1.5 is greater than 1, that's an exponential growth. Another example, 30 times 0.8 to the x power. Now, since the 0.8 is the one with the exponent, that's the number I'm looking at, and since that number is between 0 and 1, that means that would be a decay, which means it would have gone down. Okay? The 30 actually becomes what is called an initial amount, an A, that we will look at in the next formula. In actuality, I'm going to put this whole formula up here. You're going to use this formula a lot for this, and where the most of this section is going to be dealing with, say, word problems, application problems. AT equals A raised to the times 1 plus or minus R raised to the T power. Now that 1 plus or minus R represents your B, your base. Now the A represents the initial amount, the R is the rate of increase or actually decrease, depending on if it's plus or minus. T is the number of time periods, and A to the T equals the final amount. Remember that if it's 1 plus R, it's a growth factor. If it's 1 minus R, it's a decay factor. So if I'm talking about going up or increasing value, I'm going to use plus. If I'm talking about losing or decreasing value, I'm going to use minus. So look at example number 2. It's in the book on page 492. It says, Tony purchased a rare 1959 Gibson Les Paul guitar in 2000 for $12,000. Experts estimate that its value will increase by 14% per year. use a graph to find the value of the guitar when it will be $60,000. Okay, so here we go. Since we're talking about growth, we're going to say, or increasing value, we're going to say 1 plus R. And so we're going to take the 12,000, that's my initial amount because that's how much the car was worth, or the guitar was worth at the beginning. I'm going to say 1 plus 0.14. Notice how I changed the 0.14, or the 14%, to a decimal. Add that to the 1, which is just 1.14. And from this point, you're trying to find out A of t is equal to, according to the problem, we now know that this is worth $60,000. Okay, so if it's worth, we want it to be worth $60,000, that's where we want A of t to be. So we're going to use a graph and trace to find that. So we want to know when that's going to be equal to $60,000. So we would type in this function right here into the calculator and then do a graph and trace to find out when it would be equal to 60,000. Now, hopefully you bought the Inspire app that I had mentioned on Edmodo just on Friday in spring break when I found out. Sorry it was last minute and the sale was only a little bit. But even now, it's only like $30, which is still a really good deal considering that you could have a full-fledged calculator that you would have to get a little used to, but you would have all the capabilities that the normal Inspires have, and it's only $30, which is a lot cheaper than having the $150 calculator normally. But anyways, if you do that, you will find out that once you do the graph trace, that at 12.3 years, it would be worth $60,000. So it would take sometime around 2012, it would have been worth around $60,000. Okay. Next example, on number 3, talks about the value of a truck bought new for $28,000 decreases 9.5% each year. So, okay, so here we're talking about a truck, and we now know that it's decreasing its value. So that means we're going to subtract. 9.5% would have been 0.095. Actually, that should be 0.095. Okay, so then let's go ahead and hit play again. And then, again, same thing, 0.905. Okay, if I graph and trace that, I should find out that it would take me roughly 17.3 years because I'm looking for when the Y value at the bottom of the screen is equal to $5,000. And so it would take me roughly 17.3 years for the truck to decrease in value to $28,000, or from $28,000 to $5,000. That's pretty much it for this section. It doesn't get much harder or than that. So I mean, mainly that's what I would be looking for. If you have that understanding, you should be good to go. If you do have any questions, feel free to ask.